Welcome to the universe, an unfathomable realm of mystery, scale, and wonder. From our vantage point on this pale blue dot, we gaze out into the cosmic ocean, our minds struggling to grasp the sheer vastness that surrounds us. Prepare yourselves, for today we embark on a journey to explore some of the most mind-bending facts about the universe. Facts that will challenge your perception of reality and leave you in awe of the cosmos. Get ready for some mind-bending facts that redefine reality. When we talk about the universe, we must first confront its staggering size. Imagine the largest thing you can, a mountain, a continent, the entire planet Earth. Now consider that even our entire solar system, a cosmic oasis that took humankind millennia to map, is but a speck within our galaxy, the Milky Way. And the Milky Way itself, home to hundreds of billions of stars, is just one of trillions of galaxies scattered throughout the observable universe. We measure this observable universe, the part we can see from Earth, based on how far light has traveled since the Big Bang in light years. 1 light year is the distance light travels in a year, a mind-boggling 5.88 trillion miles. Hold on to your hats, because the observable universe stretches 93 billion light years across. That means that when we gaze at the most distant objects, we are seeing light that has been traveling for billions of years since the universe's infancy. Think about that for a moment. We are looking back in time, witnessing the echoes of events that transpired eons ago. But here's the kicker. The observable universe is just that, observable. What lies beyond that limit, we can only theorize. The universe could extend infinitely, filled with even more galaxies, stars, and wonders yet unknown. It's a humbling thought, realizing that we are merely scratching the surface of a cosmic tapestry far grander than we can currently comprehend. And if that's not mind-blowing enough, consider this. The universe is not static. It's expanding every single second, carrying those distant galaxies further away from us at an accelerating rate. Imagine a loaf of raisin bread baking. As the bread rises, the raisins, representing galaxies, move further apart. That's the universe we live in, a dynamic and ever-evolving entity. What does this expansion mean for the future of the universe? Will it continue to expand forever, or will it eventually contract in a reverse Big Bang? These questions continue to puzzle cosmologists and fuel our insatiable curiosity about the cosmos. The next time you find yourself on a beach, take a moment to let the sand run through your fingers. Each tiny grain represents a world, a possibility, a story waiting to be told. Now, imagine a beach so vast, so expansive, that it makes even the Sahara Desert look like a speck of dust. That's the scale we're talking about when we consider the number of galaxies in the observable universe. And astronomers estimate that there are trillions of galaxies out there. That's a 1 followed by 12 zeros. If you tried to count them all, 1 galaxy per second, it would take you longer than the current age of the universe. To put it simply, there are more galaxies in the observable universe than there are grains of sand on all the beaches on Earth. And these galaxies are not all alike. They come in a dazzling array of shapes and sizes, each with its own unique history and characteristics. Some, like our own Milky Way, are spiral galaxies with graceful arms swirling around a central bulge. Others are elliptical galaxies resembling giant cosmic footballs, while still others are irregular galaxies, defying easy categorization with their chaotic and often beautiful forms. Within these galaxies, stars are born, live out their lives, and eventually die, sometimes in spectacular supernova explosions that briefly outshine entire galaxies. And around many of these stars, we believe planetary systems like our own may exist, potentially harboring worlds teeming with life. For centuries, astronomers believed that the Milky Way was the entire universe. It wasn't until the 20th century that we began to grasp the true scale of the cosmos and our relatively insignificant place within it. Each galaxy is like an island universe, separated by vast stretches of intergalactic space. And yet, despite their isolation, these galaxies are connected. Gravity, that invisible force that holds our feet to the ground, also binds galaxies together in clusters and superclusters, forming a vast cosmic web that stretches across the universe. The more we learn about galaxies, the more we realize how much we don't know. They remain one of the most active areas of astronomical research, full of unanswered questions and mysteries waiting to be unraveled. We've just begun to grasp the scale of the observable universe, but what lies beyond its edge? Could there be more, much more, than meets the cosmic eye? It's a question that has captivated scientists and philosophers for centuries. And today, we have a theory that suggests a mind-boggling answer: the multiverse. Imagine, if you will, a vast cosmic ocean filled not with stars and galaxies as we know them, but with entire universes, each a bubble of reality expanding outward from its own Big Bang. Some might be similar to our own, governed by familiar laws of physics, while others could be radically different universes where gravity works in reverse or time flows backward. This isn't just science fiction, my friends. It's a natural consequence of some of our most advanced theories in physics, like string theory and inflationary cosmology. These theories suggest that our universe, vast as it is, might be just one of countless others, each with its own unique properties and possibilities. The implications of the multiverse theory are as profound as they are dizzying. It means that the laws of physics, as we understand them, might be just a local set of bylaws, applicable only to our own cosmic neighborhood. In other universes, the fundamental constants of nature, the strength of gravity, the speed of light, could be entirely different. Think about that for a moment. It means that the very fabric of reality, the fundamental forces that govern the universe we observe, might be just one configuration among an infinite array of possibilities. And each of those possibilities, each of those universes, could be teeming with its own unique forms of matter, energy, and perhaps even life. The multiverse theory challenges us to expand our definition of reality itself. It forces us to confront the possibility that our universe, with its familiar laws and constants, might be just a tiny island of existence in a boundless sea of cosmic diversity. Of course, the multiverse theory is still just that, a theory. We have no direct evidence yet to prove or disprove its existence, but the very fact that it emerges naturally from our best models of the universe is a testament to the power of human curiosity and our relentless pursuit of understanding. Perhaps one day we'll develop the tools to peer beyond the cosmic horizon, to catch a glimpse of these other universes, to see firsthand the infinite tapestry of reality that the multiverse theory suggests. Until then, it remains a tantalizing possibility, a cosmic mystery that continues to inspire our imaginations and drive us to explore the universe and all its wonders. Black holes, just the name conjures up images of unimaginable power and mystery. Regions of space-time where gravity is so strong, so utterly dominant that nothing, not even light, can escape their grasp. But have you ever wondered what it is that makes black holes so incredibly dense? We often talk about black holes as if they're giant vacuum cleaners sucking up everything in their path. But the truth is, a black hole is simply a massive amount of matter crammed into an incredibly small space. Think of the most massive object you can imagine and then squeeze it down to a size smaller than an atom. That, my friends, is density on a cosmic scale. This neutron star matter is some of the densest material in the universe. Imagine taking a teaspoon of this stuff. It would weigh billions of tons here on Earth. To give you some perspective, that's like compressing Mount Everest down to the size of a sugar cube. These neutron stars are fascinating objects in their own right. They spin rapidly, emitting beams of radiation from their poles. As these beams sweep across our line of sight, we see them as pulsars, cosmic lighthouses flashing across the vastness of space. But some stars are fated to collapse even further. If the core of the collapsing star is massive enough, even the resistance of neutrons can't halt the gravitational collapse. The core continues to shrink, denser and denser, until it reaches a point of infinite density, a singularity. This singularity, shrouded by an event horizon from which nothing can return, is the heart of a black hole. And it's the incredible density of this singularity that gives black holes their extraordinary gravitational pull. So, while we might picture black holes as cosmic vacuum cleaners, they're more like cosmic mountains, peaks of density in the fabric of space-time, warping the cosmic landscape around them. Black holes, with their immense gravitational pull, have captured our imaginations for decades. But have you ever wondered what would happen if you got too close to one of these cosmic behemoths? Well, my friends, prepare to be stretched, because today we're talking about spaghettification. Now, spaghettification isn't just a catchy name, it's a real phenomenon that occurs due to the extreme tidal forces present near a black hole. Imagine for a moment that you're falling feet first towards a black hole. As you approach, the gravitational pull on your feet would be significantly stronger than the pull on your head. Your body would be elongated to an absurd degree, stretched thinner and thinner, like a strand of cosmic spaghetti. But that's not all. The tidal forces wouldn't just stretch you vertically, they'd also compress you horizontally. So you're not just becoming a long, thin strand, you're also being squeezed from the sides. Imagine being stretched like taffy, your atoms themselves pulled apart by the relentless tug of the black hole. It's a rather unpleasant fate, to say the least. And as if being stretched and squeezed wasn't enough, the intense radiation near the black hole would likely fry you to a crisp long before you even reach the event horizon. But even though spaghettification might sound like something out of a science fiction horror movie, it's a real consequence of the extreme physics at play near a black hole. It's a stark reminder of the immense power of gravity and the bizarre ways in which it can warp the fabric of space-time. So the next time you find yourself contemplating a journey to a black hole, remember the fate that awaits you. Spaghettification. It's not just a funny word, it's a one-way trip to cosmic oblivion. Space, as we've come to learn, is not a silent, still place. It's a cosmic ocean teeming with energy, much of it invisible to our eyes, and sometimes from the depths of this ocean emerge the brightest explosions the universe has ever known. Gamma-ray bursts. Imagine, if you will, a single beam of light so intense, so powerful, that it briefly outshines an entire galaxy of billions of stars. That, my friends, is the raw power of a gamma-ray burst. These bursts are fleeting, lasting from milliseconds to minutes, but in that brief time, they unleash more energy than our sun will emit in its entire 10 billion-year lifespan. What could possibly fuel such cataclysmic events? Astronomers believe they signal the death throes of massive stars collapsing into black holes, or the merging of two neutron stars, those ultra-dense remnants of stellar explosions. Whatever the cause, gamma-ray bursts offer a glimpse into the most extreme environments the universe has to offer. To truly grasp the sheer energy of a gamma-ray burst, we need to take a journey into the heart of a dying star. This journey takes us to the final moments of a star's life, where the most dramatic and violent events in the universe unfold. Imagine a star much more massive than our sun, running out of fuel and collapsing under its own immense gravity. These stars, often tens or even hundreds of times more massive than our sun, have burned through their nuclear fuel at a prodigious rate, leading to a catastrophic end. The core implodes, forming a black hole, while the outer layers are blasted outwards at nearly the speed of light. This implosion is so powerful that it crushes the core into an incredibly dense point, creating a black hole, one of the most mysterious and powerful objects in the universe. This relativistic jet of matter and energy, focused like a laser beam, punches through the remnants of the star and into space, carrying with it an unimaginable amount of energy. These jets are so intense that they can outshine entire galaxies for brief moments, releasing more energy in a few seconds than our sun will emit in its entire 10 billion-year lifetime. As this jet interacts with the surrounding interstellar medium, it creates shockwaves that produce the gamma rays we detect here on Earth. These shockwaves are like cosmic tsunamis, sweeping through space and generating gamma rays, the most energetic form of light. These bursts are not merely fascinating cosmic fireworks, they hold clues to the early universe. Each gamma ray burst is a time capsule, providing us with information about the conditions and events that shaped the cosmos billions of years ago. Because they are so bright, we can detect them from vast distances, offering a glimpse into the conditions that existed billions of years ago when the first stars were forming and dying. These distant beacons allow astronomers to peer back in time to an era when the universe was young and the first galaxies were taking shape. Studying gamma-ray bursts allows us to probe the universe's history, unraveling the mysteries of stellar evolution and the processes that govern the life and death of stars far more massive than our own sun. By understanding these colossal explosions, we gain insights into the life cycles of stars, the formation of black holes, and the dynamic processes that drive the evolution of galaxies. Scientists around the world are dedicated to analyzing data from these bursts using telescopes and satellites to observe them in real time. Advanced computer simulations help us model these events, providing a deeper understanding of the physics involved. Each new discovery about gamma-ray bursts pushes the boundaries of our knowledge and drives the development of new technologies in astronomy. As we continue to explore these cosmic phenomena, we are not only learning about the universe's past, but also paving the way for future discoveries that will shape our understanding of the cosmos. The power of a dying star, as revealed through gamma-ray bursts, reminds us of the awe-inspiring nature of the universe. It fuels our curiosity and our desire to explore, to understand the vastness of space and the incredible events that occur within it. This journey into the heart of a dying star is a testament to the endless wonders that await us in the cosmos. While gamma-ray bursts are incredibly powerful, they are also incredibly rare. Astronomers estimate that only a few occur in a galaxy like ours every million years, and even then, the chances of one being pointed directly at Earth are astronomically small. But what if, by some cosmic coincidence, a powerful gamma-ray burst were to occur relatively close to our planet? The consequences could be devastating. The intense radiation could strip away our ozone layer, leaving life on Earth vulnerable to harmful ultraviolet radiation from the sun. Thankfully, the vastness of space provides a natural buffer. The closest known gamma-ray burst occurred about 1 billion light-years away, far enough to pose no threat to life on Earth. However, the study of these powerful events reminds us of the delicate balance that exists in the cosmos. Time. It's the one constant we all experience, relentlessly marching forward second by second, minute by minute, or is it? What if I told you that time, as we perceive it, is not absolute, but rather a fluid, malleable aspect of the universe? This mind-bending concept is known as time dilation, one of the most profound consequences of Einstein's theory of relativity. It tells us that time is not experienced the same way for everyone and everything in the universe. In fact, time is relative to both motion and gravity. Imagine two identical clocks, synchronized perfectly. Now place one clock on a fast-moving spaceship and leave the other here on Earth. As the spaceship approaches the speed of light, something extraordinary happens. Time on the spaceship begins to slow down relative to time on Earth. This isn't just a theoretical concept, it's been experimentally verified. Atomic clocks flown on high-speed jets have shown minuscule but measurable time differences compared to their Earth-bound counterparts. Time dilation is a real phenomenon, a testament to the bizarre and wonderful nature of our universe. But time dilation isn't just about speed. Gravity also plays a role. The stronger the gravitational field, the slower time flows. This means that time runs slightly slower at sea level on Earth than it does on a mountaintop, where the gravitational pull is slightly weaker. Of course, these differences are incredibly small, practically unnoticeable in our everyday lives. But in the extreme environments near black holes, where gravity is unimaginably strong, time dilation becomes truly mind-boggling. Imagine approaching a black hole, that cosmic abyss from which nothing, not even light, can escape. As you get closer and closer, the gravitational pull increases exponentially. Time for you, relative to an observer far away, would slow down dramatically. From the perspective of someone watching you from a safe distance, you would appear to slow down, eventually freezing in time at the event horizon, the point of no return. The concept of time dilation may seem like something out of science fiction, but it has profound implications for our understanding of the universe. It challenges our intuitive sense of time as a constant, forcing us to grapple with the idea that our experience of time is not universal. Some have even speculated that time dilation could hold the key to time travel. If we could find a way to manipulate gravity, or travel at speeds approaching the speed of light, perhaps we could find a way to journey through time itself. While the possibility of time travel remains firmly in the realm of speculation, the study of time dilation continues to push the boundaries of our understanding of the cosmos. It reminds us that the universe is full of surprises and that even our most fundamental assumptions about the nature of reality can be challenged. We often think of the universe as we see it, a tapestry of stars, galaxies and nebulae, all bathed in the faint glow of distant starlight. But what if I told you that everything we can see, all the stars and galaxies, planets and gas clouds, make up only a tiny fraction of what's actually out there? The truth is, the universe is mostly invisible. In fact, roughly 85% of the matter in the cosmos is made up of something we can't see, something that doesn't interact with light or any other form of electromagnetic radiation. We call it dark matter. We know dark matter exists because of its gravitational influence on the visible universe. Galaxies rotate faster than they should based on the visible matter alone. Clusters of galaxies are held together by a gravitational force far greater than what their visible mass could produce. This invisible matter, this cosmic web of dark matter, forms the scaffolding upon which galaxies are built and clusters assemble. It's a humbling reminder that what we see is just the tip of the cosmic iceberg. But the mysteries don't stop there. In the late 1990s, astronomers made a startling discovery. The expansion of the universe, a long-held consequence of the Big Bang, wasn't slowing down as expected. It was speeding up. Something was pushing the universe apart, a mysterious force working against gravity on a cosmic scale. We call this force dark energy, and it's even more enigmatic than dark matter. It accounts for roughly 70% of the total energy density of the universe. Imagine the universe as a balloon. Dark matter is like the material of the balloon itself, providing the structure. Dark energy, on the other hand, is like the air being blown into the balloon, causing it to expand ever faster. The nature of dark energy remains one of the biggest unsolved mysteries in modern astrophysics. Is it a property of space itself? Is it a new kind of energy field? Or is it something else entirely, something beyond our current understanding of physics? Dark matter and dark energy, these invisible forces shaping the cosmos, represent the frontiers of our knowledge. They are reminders that the universe is full of surprises and that our understanding of the cosmos is far from complete. The quest to understand dark matter and dark energy is one of the most exciting and challenging endeavors in modern science. It requires us to push the boundaries of our knowledge, to develop new technologies and new ways of thinking about the universe. As we continue to explore the cosmos, we can be certain that new discoveries await us. Discoveries that will shed light on the nature of dark matter and dark energy, revealing the secrets of the unseen universe. And perhaps in the process, we might even discover something even more profound, something that will revolutionize our understanding of the cosmos and our place within it. Space is vast, dark, and often unimaginably cold. When we think of extreme temperatures, we often picture the heart of a star, but the universe's coldest places are just as astounding. Far from the warmth of any star, in the depths of interstellar space, temperatures plummet to a frigid 2.7 Kelvin. That's about minus 455 degrees Fahrenheit, a chill that would freeze even the most resilient materials we know. These cosmic refrigerators are called voids, and they're some of the emptiest and coldest places in the known universe. Out there, molecules slow to a crawl, barely moving, their energy nearly extinguished. Now let's shift our focus from the extreme cold to the extreme heat. At the heart of every star, a nuclear furnace rages, fusing hydrogen into helium and releasing unimaginable amounts of energy. Our own Sun, a relatively average star, boasts a core temperature of about 27 million degrees Fahrenheit. But that's just the tip of the cosmic iceberg. Massive stars, many times larger than our Sun, experience even more extreme temperatures. Their cores can reach hundreds of millions, even billions of degrees Fahrenheit. These stellar giants live fast and die young, their lives culminating in spectacular supernova explosions. From the frigid depths of interstellar space to the blistering hearts of stars, the universe is a place of dramatic temperature extremes. These extremes are not merely curiosities, they are fundamental to the very fabric of the cosmos. The contrast between hot and cold drives the flow of energy, shaping the evolution of galaxies and giving rise to the conditions necessary for life. It's a delicate balance, a cosmic dance between fire and ice that has played out over billions of years, leading to the universe we observe today. We tend to think of planets as loyal companions, eternally bound to their parent stars in a celestial dance of gravity. But the universe, as always, has a few surprises up its sleeve. Out there in the vast emptiness between stars wander solitary worlds, unbound and adrift, rogue planets. Imagine a planet, perhaps similar in size and composition to Earth, but without a sun to warm its surface. It drifts through the galaxy, bathed only in the faint glow of distant stars, its surface a frozen wasteland. These rogue planets are a testament to the chaotic nature of planetary formation and the powerful gravitational forces at play in the universe. How do these rogue planets end up so alone, cast out from their stellar nurseries? The answer lies in the chaotic dance of gravity that governs the early stages of a star system's formation. Planets form from the leftover material after a star is born, dust and gas swirling in a protoplanetary disk. But this disk is a chaotic place, with gravitational interactions between protoplanets jostling for position. Some planets are drawn inward, spiraling towards their star, while others are flung outward, ejected from the system entirely. It's a cosmic game of billiards, with planets as the balls and the stakes are high. A place in the star system or a solitary journey through the void. The discovery of rogue planets has challenged our understanding of planetary systems and opened up a new frontier in the search for life beyond Earth. These wanderers hold clues to the processes that shape planetary formation and the potential habitability of worlds beyond our solar system. Detecting these elusive objects is no easy feat. Without a star to illuminate them, rogue planets are incredibly faint and difficult to spot. Astronomers rely on a technique called gravitational microlensing, which detects the subtle warping of space-time caused by a massive object passing in front of a distant star. As our telescopes become more powerful and our techniques more refined, we can expect to discover many more rogue planets in the years to come. Each discovery will add another piece to the puzzle, helping us to paint a more complete picture of the universe's diverse population of planets. And who knows, perhaps one day we'll find evidence of life on one of these wandering worlds. A testament to the resilience and adaptability of life itself, even in the most unexpected of corners of the cosmos. Diamonds, those sparkling symbols of luxury and permanence, are formed under immense pressure deep within the Earth. But what if I told you that out there, In the vast expanse of space, entire planets might be made of diamond. It sounds like something out of science fiction, yet the universe, as always, has a way of surpassing our wildest imaginations. These hypothetical worlds, known as diamond planets or carbon planets, are thought to form under unique conditions very different from those that gave rise to our own Earth. While Earth is rich in oxygen and silicon, these planets are believed to have formed in environments with a high carbon-to-oxygen ratio. The creation of a diamond planet is a story of cosmic alchemy, a tale of stellar death and transformation. It all begins with a star, much like our own sun, nearing the end of its life. As it exhausts its nuclear fuel, it sheds its outer layers into space, leaving behind a dense core known as a white dwarf. White dwarfs are incredibly hot and dense, composed mostly of carbon and oxygen. Normally, these elements would remain locked within the white dwarf, but in some cases a nearby companion star can alter its fate. If the companion star is massive enough, it can begin to siphon material away from the white dwarf, pulling it into a swirling disk of gas and dust. While the existence of diamond planets is still theoretical, astronomers have found tantalizing clues that suggest these glittering worlds might actually be out there. In 2004, scientists discovered a massive, rapidly rotating object called PSRJ 1719-1438, believed to be a pulsar, a type of neutron star that emits beams of radiation. Orbiting this pulsar, they found a planet-sized companion with a mass similar to Jupiter but incredibly dense. Based on its density and orbital characteristics, astronomers believe this companion object, dubbed PSRJ 1719-1438b, could be a giant diamond formed from the crystallized carbon core of a former star. In the vast cosmic ocean, with its swirling galaxies and twinkling stars, lies a profound question that has captivated humanity for centuries. Are we alone? This question has driven countless generations to look up at the night sky with wonder and curiosity, pondering the mysteries of the universe and our place within it. The search for life beyond Earth, for another planet teeming with life as we know it, has become a driving force in modern astronomy. With the advent of advanced telescopes and space missions, astronomers are now able to peer deeper into the cosmos than ever before, scanning the skies for signs of distant worlds that might harbor life. Our own solar system, with its diverse array of planets and moons, serves as a reminder of the incredible variety that the universe holds. From the scorching surface of Mercury to the icy plains of Pluto, each celestial body offers a unique glimpse into the complex and varied nature of planetary systems. But amidst the gas giants and icy worlds, only Earth stands out as a haven for life, a blue oasis in the vastness of space. Our planet's unique combination of atmosphere, water, and distance from the Sun has created the perfect conditions for life to flourish. Yet in recent decades, astronomers have made groundbreaking discoveries revealing the existence of thousands of planets beyond our solar system called exoplanets. These discoveries have opened up a new frontier in the search for life, as scientists now have a vast array of potential candidates to study and explore. These distant worlds, orbiting stars light years away, come in all shapes and sizes, from massive gas giants to smaller rocky planets like our own. Each exoplanet offers a unique set of characteristics and challenges, providing valuable insights into the formation and evolution of planetary systems. And among this cosmic menagerie, a select few have captured our imagination. Planets that reside in the habitable zones of their stars, where temperatures are just right for liquid water to exist on their surfaces. These so-called Goldilocks planets are of particular interest to scientists, as they offer the best chance of finding conditions similar to those on Earth. These are the potential Earth twins, the worlds that could harbor the conditions necessary for life as we know it to arise. The discovery of such planets has fueled the hope that we might one day find evidence of extraterrestrial life, or even a new home for humanity in the distant future. As our technology continues to advance, the search for another Earth will undoubtedly remain one of the most exciting and profound endeavors in the field of astronomy. Imagine a star blazing with light and heat, its energy radiating outwards into the vast expanse of space. As we move away from the star, the intensity of its radiation diminishes, creating a gradient of temperatures that define the habitable zone, often referred to as the Goldilocks zone. This metaphorical region, not too hot and not too cold, represents the sweet spot for liquid water to exist on a planet's surface. Just like Goldilocks and her porridge, the conditions have to be just right. Too close to the star and the water would boil away into a scorching vapor. Too far away and it would freeze solid, locking the planet in an icy grip. But within the Goldilocks zone, water can exist in its liquid form, a fundamental ingredient for life as we understand it. The search for life beyond Earth extends beyond simply finding a planet in the habitable zone. It's about searching for telltale signs, for chemical signatures in the atmospheres of these distant worlds that could hint at the presence of life. Imagine a telescope powerful enough to capture the faint light passing through the atmosphere of an exoplanet as it transits in front of its star. By analyzing this light, astronomers can identify the chemical fingerprints of different molecules, revealing the composition of the planet's atmosphere. The presence of certain gases, such as oxygen, methane, and water vapor in specific ratios, could provide compelling evidence for the existence of life. These biosignatures, as they're called, are like smoke signals from across the cosmos, hinting at the presence of biological activity on these distant worlds. The search for life beyond Earth is a testament to our innate curiosity, our desire to explore the unknown and unravel the mysteries of the universe. Our universe is a place of constant motion, a cosmic ballet of stars, galaxies, and celestial objects swirling through the vast expanse of space. And at the heart of this cosmic dance lies a profound truth. The universe is expanding. This groundbreaking discovery, made in the early 20th century, revolutionized our understanding of the cosmos. It means that the very fabric of space-time, the very essence of the universe itself, is stretching, carrying galaxies along for the ride like cosmic raisins in a rising loaf of bread. But what does it mean for the universe to expand? It means that the distances between galaxies are increasing over time, as if an invisible force is pushing them apart. And as the universe expands, it cools, much like the air rushing out of a balloon loses heat. This expansion, this relentless stretching of space-time, has profound implications for the ultimate fate of the universe, leading to two possible scenarios that have captivated the imaginations of cosmologists for decades: the Big Freeze and the Big Crunch. Imagine a universe where the expansion continues indefinitely, where the galaxies drift farther and farther apart, their light becoming increasingly faint and redshifted as they recede from us at ever-increasing speeds. This is the essence of the Big Freeze, a scenario where the universe continues to expand and cool until all matter is dispersed across an unimaginably vast and frigid cosmos. Stars would slowly burn out, their nuclear furnaces extinguished, leaving behind only faint embers of white dwarfs, neutron stars, and black holes. As the universe expands and cools, the formation of new stars would cease, and the galaxies themselves would become increasingly isolated islands in the vast cosmic sea. The universe would become a cold, dark, and desolate place, devoid of the light and warmth that we take for granted. The Big Freeze is a chilling prospect, a slow and gradual demise of the universe as we know it. It's a scenario where the universe fades away, not with a bang, but with a whimper, its energy dissipated across an unimaginably vast and empty expanse. But what if the expansion of the universe isn't destined to continue forever? What if the very fabric of space and time, which has been stretching and expanding for billions of years, is not on an endless trajectory outward? What if at some point in the distant future the gravitational pull of all the matter in the universe is strong enough to overcome this expansion, causing it to slow down, stop, and eventually reverse? Imagine a universe where the relentless push of dark energy is finally countered by the inexorable pull of gravity. This is the essence of the Big Crunch, a scenario where the universe collapses back in on itself like a cosmic rewind, ultimately culminating in a singularity, a point of infinite density and temperature. Picture the vast cosmos with all its galaxies, stars, and planets being drawn back into a single, infinitely small point. It's a scenario that evokes a sense of cosmic symmetry, a return to the very conditions that are thought to have existed at the moment of the Big Bang. The universe, which began in a fiery explosion of energy and matter, would end in a similar, albeit reversed, cataclysm. As the universe contracts, galaxies would draw closer together, their light becoming increasingly blue-shifted as they approach us at ever-increasing speeds. The familiar redshift, which indicates galaxies moving away, would be replaced by a blue shift, signaling their rapid approach. The cosmic background radiation, the faint afterglow of the Big Bang, would intensify, bathing the universe in an increasingly energetic bath of photons. This radiation, which has been cooling and spreading out for eons, would begin to heat up and concentrate, filling the cosmos with a brilliant, searing light. The Big Crunch is a dramatic and violent end to the universe, a cosmic cataclysm that would obliterate all matter and energy as we know it. Stars would collide, galaxies would merge, and the very fabric of space-time would be torn apart in a final, apocalyptic event. It's a scenario that evokes a sense of both awe and terror, a reminder of the immense power and ultimate impermanence of the cosmos. The universe, in all its grandeur and complexity, is not eternal. It has a beginning, and it may very well have an end. This potential end, the Big Crunch, serves as a humbling reminder of our place in the vast, ever-changing tapestry of existence. As we contemplate this possible future, we are also reminded of the many extreme phenomena that populate our universe. Black holes, neutron stars, and other cosmic entities play a crucial role in the dynamics of the cosmos. Their immense gravitational forces could be key players in the eventual contraction of the universe. Scientists continue to study these possibilities using advanced models and equations to predict the future of our universe. Theories like the Big Crunch are not just speculative, they are grounded in the laws of physics and the observations we make of the cosmos. Each discovery brings us closer to understanding the ultimate fate of everything we know. As we gaze up at the night sky, filled with stars and galaxies, we are filled with a sense of wonder and curiosity. The universe is a place of endless mysteries and profound questions. Whether it ends in a big crunch or continues to expand forever, the journey of discovery is what truly matters. Each moment we spend exploring the cosmos brings us closer to the answers we seek and to a deeper appreciation of the universe we call home. Our universe is a vibrant tapestry of energy and matter, constantly shifting and changing. But even the most dazzling cosmic dance must eventually come to an end. One possible fate, perhaps the most chilling of all, is known as the heat death. Imagine a universe where stars have exhausted their fuel, fading into cold, dark remnants. Black holes, those cosmic gluttons, have devoured everything in their reach, growing ever larger and more insatiable. In this scenario, the universe continues to expand, but its energy is spread thinner and thinner across the vast cosmic canvas. Temperatures plummet, approaching absolute zero, the point at which all motion ceases. The universe, once a cauldron of creation and destruction, reaches a state of equilibrium, a uniform sea of low-level energy. No new stars can form, no life can exist. The driving force behind this cosmic decline is entropy, the relentless march towards disorder. Everything in the universe, from the smallest atom to the largest galaxy, is subject to its inexorable grip. Think of a pristine sandcastle on a beach. Over time, the wind and waves chip away at its intricate towers and walls, reducing it to a shapeless mound. This is entropy at work, dismantling order and increasing randomness. In the vast expanse of space, entropy dictates that energy, like the grains of sand, will disperse and become evenly distributed. No longer concentrated in stars and galaxies, it loses its ability to power the cosmic engine. Stars cease to shine, black holes evaporate, and the universe becomes a cold, dark, and utterly silent expanse. The concept of heat death can be a difficult one to grapple with. It challenges our innate optimism, our belief in a universe teeming with endless possibilities. But even in the face of such a bleak future, there may be a glimmer of hope. Some theories suggest that the universe is not a closed system, that there may be other universes out there, perhaps with different laws of physics. The multiverse theory proposes that our universe is just one bubble in a vast cosmic foam, constantly expanding and colliding with other bubbles. If this is true, then even as our universe succumbs to heat death, new universes may be born, bursting forth with renewed energy and potential. While the ultimate fate of our universe remains uncertain, the pursuit of knowledge continues. By exploring the cosmos and unraveling its mysteries, we gain a deeper appreciation for the preciousness of life and the wonders of the universe we inhabit. The idea of an end to everything, even the universe itself, is a daunting concept. But what if the universe isn't ending, but rather transforming, caught in a perpetual cycle of death and rebirth? This is the essence of the cyclic universe theory, a captivating idea that challenges our linear perception of time and offers a tantalizing glimpse into the potential for cosmic renewal. Instead of a single Big Bang, this theory proposes an infinite series of them, each one marking the beginning and end of a cosmic cycle. Picture it as a cosmic dance, a grand waltz of expansion and contraction, creation and destruction, playing out over unimaginable stretches of time. After billions upon billions of years, the expansion we observe today will eventually slow down, reverse, and ultimately lead to a colossal collapse known as the Big Crunch. Imagine the universe rewinding itself, galaxies rushing towards each other, stars colliding in spectacular supernovae, and all matter compressing into an incredibly dense and hot singularity. This singularity, the culmination of the Big Crunch, would contain the remnants of everything that ever existed, a cosmic graveyard compressed into an infinitesimally small point. But this is not the end. Instead of oblivion, the Big Crunch could sow the seeds for a new beginning. The immense pressure and heat within the singularity could trigger another Big Bang, igniting a new cycle of cosmic expansion and evolution. This new universe, born from the ashes of the old, might be similar to ours, or it might be radically different, governed by new laws of physics and harboring unimaginable wonders. The concept of a cyclic universe is captivating in its elegance and symmetry. It offers a sense of balance and continuity, a cosmic reassurance that even in the face of immense destruction, there is the potential for renewal. The universe becomes less of a finite entity with a defined beginning and end, and more like a phoenix constantly rising from its own ashes. While the cyclic universe theory remains just that, a theory, it serves as a powerful reminder that our understanding of the cosmos is constantly evolving. As we continue to explore the universe and its mysteries, we may find that the end of one cycle is simply the prelude to a new beginning, a breathtaking cosmic ballet with no final curtain call. From the mind-boggling scale of the observable universe to the strange and wonderful phenomena that occur within it, we've only just begun to scratch the surface of cosmic understanding. The universe remains one of our greatest mysteries. Every answer leads to more questions. Thanks for joining this cosmic journey, and remember to stay curious.